So what I need is actually a way to estimate the test error for each of these models, M0, M1, M2, all the way through MP, so that I can choose among them. And basically, in order to estimate the test error, I have two approaches. And one approach is that I can indirectly estimate the test error by somehow computing the training error and then adjusting it. And the idea behind this adjustment is that if I can somehow adjust the training error to account for the bias due to overfitting, then that can give me an estimate of test error that's, again, based on the training error, but somehow looks more like a test error. And the alternative approach is that I can try to directly estimate the test error. And I can do that using some of the approaches that are in Chapter 5 of this book. And those involve either cross-validation or a validation set approach. And so that's a really direct approach to estimating the test error, where I fit models on part of the data and then I evaluate them on a holdout set. So we're now going to talk about both of these approaches. So CP, AIC, BIC, and adjusted R-squared all adjust the training error in order to give us an estimate of the test error. And they all can be used to select among models with different numbers of variables. So we're now going to look at a figure showing us CP, BIC, and adjusted R-squared for the best model of each size that we get using best subset selection on the credit data. So we're first going to look at this figure, and then we'll talk about how these quantities are defined. So again, this is on the credit data example. And on the x-axis here, we have the number of predictors in each of these figures. And on the y-axis, we have CP, BIC, which stands for Bayesian Information Criterion, and adjusted R-squared. And again, we'll define all three of these quantities in a minute. But the idea is, roughly speaking, we want these quantities to be small. So we prefer a model in which CP, BIC, and are as small as possible. And actually, I misspoke. We want adjusted R-squared to be as large as possible. So if I look at the shape of this curve, I can see that CP is minimized when we look at the model with 6 predictors. BIC is smallest when we look at the model with 4 predictors. And adjusted R-squared is smallest when we look at a model with 6 predictors again. So that suggests that we should use somewhere between 4 and 6 predictors. And actually, if we look at these figures a little more closely, we can see that basically these curves are more or less flat after we get to around 3 or 4 predictors. And so on the basis of these figures, I would say, I really don't think we need more than 3 or max 4 predictors to do a good prediction on this credit data. So, now I've scribbled all over the slide. Oops.
One thing, though, I mean, on this picture, it's hard to see here, but actually the curve is going up, right, as we go to the right, despite the fact it's flat.
That's right, yeah.
Unlike the RSS curve.
Exactly.
Yeah.
It's a little hard to see,
yeah.
But this is slightly increasing. It's smallest with 4 predictors, and then it goes up a little bit. But, I don't really think that there's compelling evidence here that 4 is really better than 3 or better than 5. So if it were me, I think simpler is always better. So I'd probably choose a model with, 3 predictors, maximum 4 predictors.
Yeah, agree.
Great. So now we're going to talk about mallow CP. And once again, this is an adjustment to the training R-squared, the training RSS that gives us an estimate for the test RSS. And it's defined in this formula. So let's say we're looking at a model with D predictors. So then we're going to calculate the RSS for that model with D predictors. And we're going to add to the RSS 2 times D, where again D is the number of predictors, times sigma hat squared, where sigma hat squared is an estimate of the variance associated with each error epsilon in the linear model. And so the idea is we can calculate CP for those models M0, M1, M2 through MP that we were looking at a few minutes ago, and we can just choose the model with the smallest CP. So like if we're looking at the model M3, then that model contains 3 predictors and an intercept. So that model has D equals 4. And we can calculate the RSS for the model M3. And we just calculate sigma hat squared. There's a formula for that. It gives us a CP. And out of all of these models, M0 to MP, we're just going to choose the one for which the CP is smallest, because that's the one that we believe is going to have the smallest test set RSS.
Now, just to clarify a bit about the sigma hat squared, first of all, if P is bigger than N, we're going to have a problem, right? Because typically sigma hat squared, the same values, the same estimate is used for all models being compared. So usually what you do is you fit the full model, all P predictors, and you take the mean square residual for that model to give you sigma hat squared. So that's the way you do it. And of course, that's going to create a problem when p is bigger than n because that full model was not defined and the error will be 0. So already we see that CP is restricted to cases where you've got n bigger than p.
That's right.
And even if p is close to n, you're going to have a problem because your estimate of sigma squared might be far too low.
So that's Mallow's CP. And then another very closely related idea is called the AIC criterion. So the AIC stands for Akaike Information Criterion. Akaike was the name of the guy who came up with this idea. And the way that this is defined is negative 2 log L plus 2 times D, where D is once again the number of predictors in the model that I'm looking at. So for M3, D equals 4. And now capital L here is the maximized value of the likelihood function for the estimated model. So this looks a little bit complicated, and in fact it's written in this very general way because AIC is a quantity that we can calculate for many different model types, not just linear models, but also logistic regression and so on. But it turns out that in the case of a linear model, negative 2 log L is just equal to RSS over sigma hat squared. So if you look at that and you plug in RSS over sigma hat squared for negative 2 log L, then what you realize is that AIC and Mallow's CP are actually proportional to each other. And since we're just going to choose the model for which CP is smallest, that's equivalent to choosing the model for which AIC is smallest. So AIC and CP are actually really the same thing for linear models. But for other types of models, these things are not the same, and AIC is a good approach. So we've talked about CP and AIC. And another very related idea here is the BIC, where B stands for Bayesian. So this is the Bayesian information criterion. And it's like the AIC and this Mallow CP, but it comes from sort of a Bayesian argument. And once again, we've got a very similar formula. We calculate the residual sum of squares. And then we add an adjustment term, which is the log of the number of observations times D, which is once again the number of predictors in the model I'm looking at. So like M3, since it has 3 predictors and an intercept, M3 has D equals 4. And once again, sigma hat squared is an estimate of the error variance, which may or may not be available depending on whether n is greater than p or less than p. And so once again with BIC, we're estimating the test set RSS, or rather the average test set RSS across the observations. And so we want it to be as small as possible, so we're going to choose the model with the smallest BIC. So what's the difference between BIC and AIC? Well, remember, AIC, it would look just like this, but in AIC, this term was actually 2D sigma hat squared, right? So the only difference between AIC and BIC is the choice of log n versus 2. BIC has this log n here, and AIC has a 2. And so in general, if n is greater than 7, then log n is greater than 2. And so what that means is that if you have more than 7 observations in your data, BIC is going to put more of a penalty on a large model. And in other words, BIC is going to tend to choose smaller models than AIC is. So BIC is going to give you the selection of models that have fewer variables than either CP or AIC. So we see that these 3 ideas, BIC, CP, and AIC, are really almost identical. They just have slightly different formulas. We want to minimize them, and they all require an estimate for sigma hat squared, which again is not available necessarily if it's only going to be available if n is greater than p. So the last of these approaches that I'm going to talk about that sort of indirectly adjusts the training error to get an estimate of the test error is the adjusted R squared. And so we saw in Chapter 3 the idea of the R squared. And remember, R squared was defined, just as a little refresher, R squared is defined as 1 minus the residual sum of squared divided by the total sum of squares, where, in case we need a reminder, the total sum of squares is just the sum of yi minus y bar squared. So y bar is the average response, yi is the ith response, and we're just taking the sum of those squared values. And so this was the r squared, and as we know, a big r squared indicates a model that really fits the data well. But unfortunately, you can't compare models by just taking you can't compare models of different sizes by just taking the one with the biggest r squared, because you can't compare the r squared of a model with 3 variables to the r squared of a model with 8 variables, for instance. So the adjusted r squared tries to fix this. And the way that it does that is that it makes you pay a price for having a large model. So the idea is adjusted r squared adjusts the r squared so that the values that you get are comparable even if the numbers of predictors are different. So the way that it does this is by adding a denominator to RSS and to TSS in this ratio. So instead of just taking 1 minus RSS over TSS, we take 1 minus RSS over n minus d minus 1 divided by TSS over n minus 1, where again, d is the number of variables in the model that we're considering. And so basically the idea here is that when d is large, this denominator is really large, and so you're dividing the RSS by a really big number, and you're going to end up with a smaller r squared. So what's happening is that we're going to pay a price for having a large model in the adjusted r squared, unlike the classical r squared, where we pay no price for having a large model with a lot of features. So the adjusted r squared, we want it to be large. If it's large, then that indicates a model that really fits the data well. And again, the idea is that adjusted r squared is something that we can actually compare in a meaningful way, regardless of the number of predictors in the model.
Somebody just noticed, looks like it doesn't require an estimate of sigma squared. That's good. And you can also apply it when p is bigger than n.
Yeah, that's right.
Good.
So that's a really nice advantage of RSS. As Rob said, we don't need to estimate sigma squared, which can be a problem. And in principle, we can apply it when p is larger than n. So we want a large value of adjusted r squared. And so the adjusted r squared, in practice, people really like it. It tends to work really well. So some statisticians don't like it as much as CP, AIC, and BIC. And the reason is because it sort of works well empirically, but some statisticians feel that it doesn't kind of have the theoretical backing of some other approaches. Right. What do you think of that, Rob?
That's true. There is a bias in our field towards things which have more theory behind them. And I guess this is an example of that.
But one nice thing about adjusted r squared is, like, if you're working with someone who's not a statistician, like scientists who aren't statisticians are really familiar with r squared. And so when to understand r squared, adjusting r squared is just a really small one-off, and it's kind of easier to explain to someone in a certain sense than AIC, CP, or BIC. And so that's one really nice thing about it. But adjusted r squared, you can't really generalize to other types of models. Right. So if you have like logistic regression, you can't do this.
So you'll see in the next section we'll talk about cross-validation, which is our favorite method, which you can generalize. And one major advantage is you don't need to know D. So the D in this method, in adjusted r squared and CP and AIC, is the number of parameters. But in some methods like ridge regression and the lasso, which we'll also talk about again in a few minutes, the value of D is not even known. So we can't apply any of these methods, but cross-validation can still be applied.
Yeah, that's true. So like in this whole discussion, I've been talking about least squares models, and then I've been occasionally mentioning logistic regression. But I could have some totally crazy model that I come up with that like is like something that nobody's ever seen before, and it would be totally hopeless to apply an AIC type of idea to it or an adjusted r squared type of idea. But I can always perform cross-validation or the validation set approach, no matter how wacky my model is. And that's actually a really nice thing about those two approaches.